So, second unit was Newton's laws of motion, all three of them, which is really just about forces. So first off, the first law, usually called the law of inertia. The idea here is that the natural state for things is not to slow down and stop. So if we're trying to explain, what force is it that keeps an object moving, we're probably off base there. An object doesn't need a force to keep moving. It keeps moving because that's what objects do naturally. The natural state is to keep moving if they're moving, to maintain constant velocity. If it's at a velocity of 0, it stays at a velocity of 0. If it's at a non-zero velocity, it keeps that non-zero velocity, constant speed, constant direction, forever, until acted on by an unbalanced external force, or a series of unbalanced external forces. Now, first law is really, at this point, unnecessary, because the second law equation includes this. If we have, in the second law equation, if we have net force of 0, we get acceleration equals 0, which is all this is saying. Constant velocity is the same as saying acceleration is 0. So the second law equation, much more heavily used. If the special case of this, where acceleration is 0, that's Newton's first law. This is just a more general version. So we have the two different forms of it, the net force with the sigma symbol or with the subscript net. Either way, it means the same thing. So in solving a problem like this, we would just replace that sigma f with all the forces that act in whatever direction we're examining right now, add it together, and we need to be careful about direction. So one direction is positive, the opposite direction is negative. Don't mix and match dimensions on this. So do just x forces or just y forces, and x acceleration and y acceleration correspondingly. We'll do more on that in just a minute. The third law, often called action-reaction, the law of action-reaction, which is a silly name for it, because reaction sounds like it happens after the action, or like the action causes the reaction. Really, this is just saying that forces come in pairs. So a force is an interaction between two objects. When they interact, they each experience that force. So if we've got, say, friction between the floor and a book, slide a book across the floor gets a frictional force from the book, and the book gets a frictional force from the floor. Right now, we're all being pulled downward by the earth. The earth is being pulled upward by all of us through a gravitational interaction. The floor is pushing up on your feet, and your feet are pushing down on the floor. Those are all Newton's third law pairs. Non-examples would be things like gravity is pulling me down and the floor is pushing me up. Those two forces happen right now to be equal in size and opposite in direction. They're not a Newton's third law pair, though. So the gravity part, I'm pulling up on the earth and the earth is pulling down on me, that's a third law pair. The floor is pushing up on me, I'm pushing down on the floor, that's a third law pair. So it's always object A pushes on object B, and object B pushes on object A. That's the third law pair. So think about the objects involved there. That'll help identify those. You probably won't have to do a problem on the AP exam that says, name the third law pair of forces here. Instead, it'll just be part of the problem. So you'll have two objects, and maybe there's a frictional force between them. Then you'll have to recognize, oh, they each get a frictional force. So when I do a free body diagram for both objects, they both have that frictional force, same size, opposite direction. We looked at the four common forces that show up in tons of problems like this. We've got force from gravity. That's really the force from the earth. It's a type of force called gravity. But, it's a downward force, or toward the center of the earth. And we have this equation to calculate it. We do the mass of the object, the small object, not the mass of the earth. Mass of the small object times g, which is the gravitational field strength, or the acceleration due to gravity, same quantity. That's always straight down, straight toward the center of the earth. We've got normal force. Remember, normal is a geometry word. It means perpendicular. So it's perpendicular to, or normal to, whatever surface is causing it. It's a contact force. So if we don't have contact between an object and some surface, we don't have a normal force. So like a block hanging from a string but not touching the ground or a wall, no normal force there. Frictional force. We actually have two different types of frictional forces, kinetic friction and static friction. We'll get more into that in just a bit. But we can calculate the magnitude of the frictional force, or if it's static friction, the maximum magnitude of the frictional force by doing mu times the normal force. Now, in a lot of these problems, the gravitational force and the normal force are equal to each other. So that's if an object is on a horizontal surface and it's not accelerating upward or downward, and those are the only two forces acting on it. That's the case where those two forces are equal to each other. They don't have to be, they just happen to be frequently. But as a result, I think people get into the bad habit of just saying frictional force is mu times the gravitational force. That's not the case, and we don't want to evaluate it that way because there are plenty of cases where normal force and gravity force aren't equal. Frictional force opposes sliding of surfaces. Sometimes that means the frictional force will be opposite the direction of an object's motion. Sometimes it's in the same direction as an object's motion. So the big example of where that's not opposite of motion is for a car. Your car can accelerate forward by turning the wheels. Because there's friction between the wheels and the road, your car is able to pull itself forward. So there's a frictional force forward when you're accelerating in your car, acting on your car from the road. Without that frictional force, we just sit there and let our wheels spin like on a really icy day. A lot of the time, friction will oppose motion, but not always. It always will oppose sliding. So that wheel spins on the surface of the ground. Well, that's sliding of one surface past another. Friction opposes that sliding. So in order to get that wheel to stop sliding, it needs a frictional force opposite the direction that that wheel is spinning, which it happens is in the forward direction, or in the direction that the car is going to be moving. So you just need to watch out for those little distinctions. Last one, we have tension, Ft. Tension is present whenever we have a rope or cable or chain, and it's always a pulling force in the direction of that rope or cable or chain. So we never push with a rope, and we don't have any component of the force perpendicular to the rope. It's always straight along with the rope. So if I threw a lasso at you and connected us with a rope, the only force I could apply to you would be directly toward me. So I couldn't push you with that lasso or shift you off to one side or the other unless I moved all the way around and started pulling you in a different direction. Don't worry, I don't have a lasso. I do have a whip, you're right, but I don't have a lasso. And the whip is just for demonstration purposes in the sound unit. Current students, you haven't seen that yet. All right, free body diagrams. Remember, on the AP exam, they will have a question on the free response section that gives you one part is draw a free body diagram for this system, or for this situation. So those four forces that we talked about, those show up pretty commonly. They may tell you that there's an extra force, maybe even give you a label to use for that. An extra force F is applied, so that would show up on a problem like that, or on a diagram like that. Be careful with these free body diagrams. The rules that they have in place for free body diagrams, they're pretty hard and fast. So the rules are that the forces have to start, the arrows have to start at the dot and point away from the dot. If your arrow points toward the dot instead, they don't give you the point for that force. They also say that those forces have to be labeled. So if you have an arrow but no label, if we have an upward force on that one but no Fn, we don't get the point for that one. They also say that we need to include our forces as whole forces and not components of forces. So like here in this diagram, we have a gravitational force downward acting on that block on the ramp. We split that up into the part that's perpendicular to the ramp and the part that's parallel to the ramp. But if we are asked, part A, draw a free body diagram for this, don't include those two components of the force, just the overall Fg pointing straight downward. Grading on this always goes the same way. It's 1 point for each correctly drawn force, and -1 point for each incorrectly drawn force, and then 0 points if you just don't include the force. So if you miss a force, you don't earn 1, but you also don't lose 1. When you draw components of a force, they treat each of those as an incorrectly drawn force. So I would get +1 point for having the gravitational force downward, and then -1 for that component and -1 for the other component. net point, then I'd lose a point for that force. So if you want to break a force up into its components, that's fine. Just don't do it on the dot that they draw for you, where they say, draw your free body diagram here. They give you those directions in the problem. Draw whole forces only, not components of forces. It'll say that right in the problem. So they're not trying to trick you into drawing it the wrong way, but you got to pay attention to the directions on that.
So you can't draw components at all?
Not on that part. Later on, if you want to think of having a pretty diagram for them and a working diagram for you, that's fine. You can do whatever you want on your own diagram. You can include that, and if you've got that information, that's useful. They don't have that on the grading guide one way or another, so either way is fine for that. Other thing that people get caught on for free body diagrams is drawing things that aren't forces. Only forces go on there. So velocities, accelerations, distances, those things don't go on a free body diagram. So that first diagram on the left, maybe it's moving to the right. If we drew an arrow to the right and labeled it velocity, and labeled it V, we're losing a point for that, because that's not a force, doesn't go on a free body diagram. I think we have a few things to look out for when you're drawing these. If you have two objects, sometimes that shows up. Like the last example, there were two objects there. We could draw a free body diagram for each one. If we have an interaction between those two objects, make sure that you have that interaction, that force, drawn on both objects. That's a Newton's third law thing. Objects interact with each other. We have pairs of objects that interact, and we call that interaction a force. If you can't pick out a second object that's causing that interaction, you probably made up that force. So like a car going around a turn, this is a really common one. People will say, oh, there's an outward force that pulls things toward the outside of the car. Well, if you can't identify an object that started pulling on that object when your car decided to turn, which you shouldn't be able to, then that force isn't present. The objects don't get pulled to the outside of the car, they just try and go in a straight line. The car is turning to the left, though. So it's not that the objects move to the outside of the car, it's that the outside of the car moves toward the objects. The other piece here, when you're drawing these diagrams or setting up Newton's second law, we do a lot of problems where acceleration is 0 in one dimension or the other. Evaluate that every time, though. So don't assume that if I've got a force to the right and a force to the left, they have to be the same size. They may not be. If acceleration in that dimension is 0, yeah, they are. But think about that first. Do I have the information here that there's no acceleration in that dimension? When we do systems, that's where we group objects together and treat them like one big thing. And at first that seems like, why should we be able to do that? But remember that when the box gets pushed, there's really lots of little tiny pieces of the box, and they're being held together by lots of little tiny forces. So we actually do this every time. The idea with the system is that there are smaller components to it. There's an internal structure to this. The technical definition for an object in physics is something with no internal structure. You really have to go very small scale before something truly fits the definition for object, like quarks. Quarks behave as objects, and electrons behave as objects. So we can't even go down to atoms, because we know that atoms have smaller pieces. Even protons and neutrons, those are made up of quarks. So, a true object is very, very small scale. But oftentimes, the internal structure of a collection of objects, like a box, oftentimes that doesn't matter. It's not going to change during the problem. Those forces don't affect our problem. So calling a box an object, not the worst thing you can do until we get into a situation where, say, we're pulling a box in two different directions and the box is going to rip apart. Well, that object couldn't rip apart because objects can't be divided into smaller pieces. So then it makes sense to think of the box as being, multiple pieces. In any of these system choices, though, we can say that the acceleration of that system as a whole is due to external forces. So when I've got my student pushing the box on a wild and crazy Friday night like this one, how you guys like spending your time, student pushes that box, we have to think about the force from the student on the box, we have to think about the force from the floor on the box. the force from the Earth pulling down on the box, we don't have to think about the force holding one atom attached to the next atom within the box. That's important for keeping the box together, but it doesn't make the box as a whole accelerate from place to place. So it's only external forces that cause acceleration on that system. Okay, and that's actually it for the review part. One last thing that I want to talk about, though, I thought I had more about the static friction or kinetic friction on here. That frictional force on the equation sheet is written as FF is less than or equal to mu times the normal force. So remember, the idea there was that if I have like my coffee cup sitting on the table right now, I'm not touching that coffee cup. There's no horizontal forces acting on it. If I said that there was a frictional force acting horizontally on that cup right now, it'd be the only force on it. So my cup would have to be accelerating one way or the other, which would be weird. It's only when I apply a horizontal force to this cup, just a little tiny horizontal force right now, and the cup doesn't move, that it makes sense to say, yeah, there's a frictional force. Because if there weren't a frictional force, my hand pushing on it would be the only force acting on it, and it would be accelerating. Now I can apply a really tiny force or a little bit bigger force without making this cup accelerate. That force between the surface of the cup and the surface of the counter, that force can vary in size depending on what other forces are present. So when we do mu times normal force, and the mu is the static coefficient of friction, that value is the maximum that that static frictional force can get to. Not necessarily what value it's at right now. Right now, not touching the cup again, that force is at 0. We still have some value for mu between the cup and the table, and some value for normal force between the cup and the table. When we multiply those together, though, that doesn't tell us the force right now, it tells us the maximum that force can be. Then all I have to do is apply a force bigger than mu times the normal force, and that cup starts to accelerate. It starts to slide across the counter. Now we switch from static friction to kinetic friction, which is smaller than the maximum value for static friction. So as soon as I get that moving, this thing gets easier to push. Remember, the idea there was that all those little bumps and grooves that make up the surface, they're bouncing across each other now. They're not locked in place, and you have to exert a lot of force to get them moving. They're just kind of bouncing across each other as it slides. All right, well, with that, we are done with the review on the Newton's laws, so we can do some more practice with those.